part 2 of chapter 10. So, as we said in part 1, the definition of period here is the number of seconds that it will take to do one complete rotation, or T over N, and it is in terms of seconds. So the units is second in SI unit. If you remember, omega, or the angular velocity, was delta theta over delta t. The change in angular position over the time of this change will give you the angular velocity. So if you do one complete rotation, the change of theta would be 2 pi for you, 2 pi radian, right? And the time, if you do one rotation only, the time will be equal to the period of the rotation. So I'll have t here. Okay, so I can write omega 2 pi over t. Okay, if you're looking at this, frequency was 1 over t as well. So the frequency and the period had this type of relation. So I can use this, okay, and write omega to be 2 pi 1 over t, and 1 over t could be frequency. So I can write omega being 2 pi times frequency. These are very helpful, especially these two. Okay. We also notice that we have a average angular acceleration here, or alpha average, which is the change of the angular velocity over time. Just like what we had before on the one-dimensional motion, not on a circle, we had the A, or the acceleration, being equal to delta V, change of the velocity, over delta T, over the time of the change. Okay? We have the same thing here. And these are, by the way, all vectors. So delta omega over delta t will give you the average angular acceleration. Okay? Now, let's take a look at what we mean when we have an increasing in the speed or rotation, or decreasing in the speed or rotation. So for a fixed rotation axis, which we can see right here. So this is the axis of the rotation right there. And angular acceleration and angular velocity vectors both lie along the axis. So in other words, if I have omega being in that direction upward, so it's a positive omega in this case, okay, so omega is positive, and acceleration is also being positive, so alpha is also being positive. They're in the same direction, so it will speed up. If you have alpha being in the opposite direction of omega, then it will slow down. So here, omega is positive, but alpha is negative. Okay? In other words, if you remember from our one-dimensional motion or two-dimensional motions, if you multiply A by V and you get a positive number, then you know that you are gonna speed up, or your velocity and acceleration are in the same direction. But if you multiply them and you get a negative number, then it means that you're gonna slow down. Okay? Kind of like that. It's the same here, alpha times omega being positive, like that. They're both positive, so if you multiply them, you're gonna get a positive number. So you're gonna speed up. If you multiply them and you get a negative number, then you're going to slow down. Okay? Now, it's the same here. So you can see in this picture on the right side. So in the instantaneous angular acceleration is technically delta omega over delta t when delta t goes really small, goes close to 0, and I can put a limit here. The limit of delta omega over delta t when the limit is 0. In other words, if you take a derivative of omega with respect to t. Okay, the unit for that is the same, radians per second square. It's the same for here as well. Radians per second square, or radians over second square over S2. Okay, so if you're looking at this, omega is positive, alpha is positive. That means that if you multiply them, you're going to have an increase in the speed, or you're going to speed up. Okay, here they have the opposite signs, so you'll slow down. Here, if you multiply alpha and omega, you're again going to get a positive value because they are both negatives. So it will speed up again. Well, speed will increase, but in the negative direction. Okay, so remember this, that we had this counterclockwise, omega was positive, and clockwise, omega was negative. Okay. And if, again, one is positive, the other one is negative, you are going to have the speed to slow down and to speed to decrease. So let's take a look. We have a change of velocity here. So we have a 33 revolution per minute. Okay, so the velocity at the beginning is 33 revolution per minute. Okay, so in 60 seconds, it will do 33 revolutions. And it went up to 78 revolution per minute. And the time for that to happen was 3 seconds. What's the average angular acceleration in MKS units? And MKS is just this I units, right? Meters, kilogram, and second for time. So in other words, we are looking to find alpha. Alpha is delta omega over delta t, okay? And delta omega is omega 2 minus omega 1. And they are both positives. So I do care about them being a vector, but here they're both positives and they're in the same direction. And delta t is 3 seconds. So I have 3 here. Omega 2 is 78. Omega 1 is 33. And if you put that in your calculator, 78 minus 33 is 45. Okay. And delta t is 3 seconds. Now, alpha equals, so 45 revolution per minute over 3 seconds. Okay, so now I need to play with the units a little bit. Okay, so far the method is correct, but we have to be able to change this a little bit. So let's see how I can do this. So 3 seconds is for delta t, that is correct. 45 revolution in 1 minute versus 1 minute is 60 seconds, and 1 full revolution will be 2 pi radian. Okay, so now you have alpha being equal to 45 times 1 times 2 pi over 60. And let's see what the unit is. So this minute and this minute will cancel out. This revolution and this revolution will cancel out. So you have radian per second here. Okay. Now, if you want to write it in a clear way, you have 45 times 2, which is 90 pi. Okay. You have 3 times 60, which is 180. And this is also in seconds because it's 3 seconds. So you have radian per second, or you have radian per second square. Kind of like that. Okay, so now you can also say that your alpha is pi over 2 radian per second square. Okay, let's take a look at this. We have a gymnast on a high bar, and the gymnast on a high bar swings through 2 revolutions in a time of 1.9 seconds. So we have 2 revolutions in 1.9 seconds. That's what we have. Find the frequency. So we're looking for frequency to see what the frequency is. And the average angular speed of the gymnast. So average angular speed, omega. These are the 2 things that we're looking for. So frequency is the number of turns over time, okay? And this number is just a number. It does not carry any meaning associated with it. But this second is in terms of seconds, right? This is in units of seconds. So you have 1 over seconds, or as I said, second to the power of -1, or hertz, okay? So the frequency is 2 revolutions in 1.9 seconds. 2 full circular motion in 1.9 seconds. Okay, so if you do that, you will get 2 over 1.9 will give you 1.05 hertz. That's the frequency. Okay, now if you want to find omega, remember that omega was delta theta over delta t. Okay, or you could write it like this, 2 pi over t, or you could write 2 pi frequency. So I am going to use this. Omega is 2 pi times frequency, or 2 pi times 1.05. Okay, if you do that, then you will have 6.6, okay, close to 6.6, and this is radian per second for the speed. So we have, that's our angular speed. All right. Okay, let's take a look at another example. So we have an airplane jet engine here, and it says the fan blades are rotating with an angular speed of -110 radians per second. So this negative means that they are going in this direction. They are doing clockwise. So that's why the omega is negative. Okay, so clockwise, the omega is negative. So omega 1 is -110 radians per second. And as plane takes off, the angular velocity of the blades reaches, so the second one is -330 radians per second. And the time of delta t equals 14 seconds. Okay. We're looking for find the angular acceleration, assuming it is constant. So angular acceleration, alpha, is, and it's average, okay? But we know if something is constant, its average and its instantaneous value would be the same. So I could use average here, or I can just use alpha. Remember, if something is constant, its instantaneous value and its average value are the same. So if something is constant, like alpha, its average value and its instantaneous value would be the same because it's constant, doesn't change. So I have delta omega over delta t, and alpha is omega 2 minus omega 1 over delta t. So I have negative 1, 1, 10 minus 330, or it has to be the other way around actually. So alpha is omega 2, negative 330, negative 110 over 14. So alpha is negative 330 plus 110 over 14. Okay. So you can write alpha being 330, it will be 220, and it will be a negative. 14 is the same. So let me real quick do this. 220 divided by 14, and it is 15.71 radians per second square. So rotational kinematics, as I said, we did use the motion in the one dimension or two dimension as just the normal kinematics that we used. We can do the same, we can apply the same type of formulas, but this time to a rotational motion. Okay, remember that I said an angular position, or theta, is omega t plus theta 0. We proved that way up here. If I can find it. Just to show it to you right here. So x was vt plus x0. We do the same thing for rotation. We have omega equals theta equals omega t plus theta 0. Okay, so you can apply the same stuff to get the rotational kinematics and solve problems with it. For example, for this one, we have a pulley over there, and an object, a box, is being attached to it with a rope. Initially, they are at 0 angular speed and 0 tangential speed. So both omega and v, they're both 0. Okay, as this box is being released and falling down, we have a negative angular acceleration and negative angular speed, because this is doing a clockwise motion. So both of them are negative, and the reason that alpha is also negative because this is an increasing in the speed. The speed is increasing, the omega is increasing as this object is falling down. So the alpha is also negative. Okay. Now, if I do that, then all of the formulas that I had between the linear kinematics or along one or two directions, I can apply those to the rotational kinematics, okay, or to the rotational type of motion. So for example, in a linear type of motion, we have a of x, here we have alpha. We have v, we have omega here. We have x, we have theta, okay? So the same type of formulas. A will go to be alpha. T would be the same. T wouldn't change. V will change to omega, okay? X will change to theta. So we have all of those, all right? We know the formula for the linear type of motion, a linear acceleration. So we can transfer everything, all the formulas that we have. Remember this? This is time independent formula that we had in the first few chapters. I can write it as the same, but instead of v, I use omega, and instead of x, I use theta. So, tangential speed. And we talked about it before. Remember that I said your tangential speed is the speed that is tangent to the path or to the circle, because we are doing a circular motion, okay? And if you remember, I said if you consider this to be your circle, but you're looking at it from the side, okay, then this is your omega, okay, and this is r. This is your r. So then this will be your, let me actually draw r in a little bit different position. So this is r, okay, and so you have r here, you have omega, which is a positive number here, then this would be your tangential velocity, okay, and in order to find that value for it is r times omega, okay, in order to be able to understand its direction, you need to do a cross product between omega and r. And I completely explained how you should do it in part 1 of the video. So if you are watching this and if you don't remember this, please go and watch the first part of the video. Okay, so the tangential speed is always tangent to the path or to the circle. Okay, now, as I said, the value for it is r omega. And in order to find its direction, it's omega cross r, but it's just a speed, it's a regular speed that we used to have. So it's meters per second, it's not radius, okay? It's meters per second for the unit for this tangential speed. Centripetal accelerations, we used to remember this, right, from the first few chapters when we were talking about the circular motion. Now, if this is also always to the center, towards the center of the motion. Okay, so if I have a circle like that, and then I can easily say that this is, for example, the center, and I have this to be the radius. And if this is moving, even if it is moving in a constant velocity, okay, let's say that this v is a constant value, okay, and here I have this to be the tangent, so v2 and v1. So even though v2 equals v1 and the value is constant, but you remember, since the direction of the velocity has changed, we have a delta v here. This delta v is not 0, even though the values are the same for both of them. But since the direction of them has changed, then that means that this value is not 0 because they are vectors. Okay, so you have two vectors. One is v1, for example, right here. The other one is v2, okay? And delta v, which is v2 minus v1, is not 0, okay? That's your delta v. And it is not 0 because it has a direction. It needs some sort of direction. And then when you find this to be your centripetal acceleration, you found that it was v squared over r, okay? And the unit for that was meters per second square, right? So, and it's always towards the center. And so I understand that the A of CP is delta V over delta T, and it is V squared over R. This V is the same tangential speed. This V is the tangential speed from before. And we know that this V is R omega. We know it. Okay, this is angular velocity. Okay, so A is V squared over R, and R omega is V, so I have to square it over R. So this R and this R squared will cancel out. I'll have an R left, and I have R omega squared. Okay. So I can also write this as R omega times omega. And then this guy is V again, right? So our centripetal acceleration is V squared over R, which I write it as R omega squared, which is equals to V omega. Okay, and I am putting this in a circle or in a box. This is very important. So remember it. Okay, and now all of these are vectors. So you need to put a vector on top of everyone. All right, so unit for that is meters per second, remember. It's not radian per second squared, it's meters per second squared. There is a relationship. Now, I'm going to introduce one more type of acceleration to you, and it is the tangential acceleration. So centripetal acceleration, which we saw from here. Okay, let me actually go back to show it to you. Centripetal acceleration here, R omega squared, or V times omega, or V squared over R. These are, which is right here. It is due to the changing of the direction of the motion, okay? Because if this motion has changed its direction, okay, you have velocity in that direction, V1, and then the V2 is in the other direction. Even if they are constant, their values or their magnitudes are constant, but you are dealing with a change in the direction. So this is due to the change of the direction, okay? Now, if the angular speed or alpha, angular acceleration, okay, or alpha is changing, you have this. Remember this? Alpha is upward, which is the angular, and alpha was, you had it right here, alpha was delta omega over delta t. This is angular acceleration. Okay, this is due to the change of the acceleration, angular acceleration. So if this one is positive, that means that it's increased in speed. If this is negative, it means it will slow down. So the relationship between these is this. This is what we had before, and this is alpha is angular acceleration. Okay, now we have a tangential acceleration. So the tangential acceleration is related to alpha through this, and this is due to the changing of angular speed. If the angular speed is changing, then you have this tangential acceleration. In other words, if you want to look at this, the A of CP, or centripetal acceleration, is always towards the center, okay, is V squared over R. It's R omega squared, or V omega, okay? We know what V is, which V is R omega. And then we have alpha, which is angular acceleration, which is delta omega over delta t, okay? But then we also have a sub t, a acceleration tangent to the path or to the circle, which is r alpha. Radius times the alpha. This is the tangent acceleration. Tangent acceleration, as we have it right here. Tangent acceleration of a rotating object. Okay, this is due to change of angular speed. Okay, this is the end of part 2 of the video. We'll come back with this example and more examples in part 3 of the video.